So as you will see, we'll find a lot of similarities with what Carsten just presented. I think the flavor of what we were trying to do is slightly different. So let me talk about the framework in which we will work. So the idea was to look at potential anomalous coupling of electrodynamics to extrascalar degrees of freedom, because as David and Carsten mentioned, it's quite natural to expect such non-minimal, non-standard couplings to appear when you have like scalar fields in your theory. So here I've written a generic action with the electromagnetic field here coupled to a field phi by a coupling H. And as Carsten mentioned, the coupling of the electromagnetic field to charged particles or to currents has to be standard here. This is required by, if you want to preserve your U1 gauge invariant for the electromagnetic field. I haven't specified the gravitational part of the actions and all the other fields because really what we were trying to do here was to find what can we say generically about cosmological observables when such couplings, conformal couplings, are present, irrespective of the dynamics of the fields, the nature of the theory of gravity, because there are various choices, various preferences from people for these theories of gravities, and we didn't want to get into building models of this part of the action. From now on, I will work in FLRW, and the electromagnetic field will be a test field, so we are in late-time cosmology matter-dominated, because all the observations I will talk about are in a matter-dominated epoch. And as I said, we're looking for generic cosmological constraints on observables that can help us constrain these couplings H here. All right. So when you do that, of course, you obtain, as Carsten pointed out, modified Maxwell's equations, which take this simple form in the case of the conformal coupling. It's much simpler than in the deformal case, as you can see. Then we, of course, pick up the Lorentz gauge. And the first thing one does to get an idea of the physics behind it is to do a geometric optics approximation. So I remind you here, you just expand before potential in terms of the small parameter alpha, which parameterizes the ratio of your wavelength to the curvature scale manifolds. And then separating orders, we find that photons actually follow null geodesics, so that will be important in the next slide. But the photon number, which is usually given by the amplitude square here times the knot component of the wave vector k, is not conserved. There's a source term here coming from the possible variations of the conformal coupling. So in FRW, that means the photon number in the geometric optics approximation takes this extremely simple form here and depends on the derivative, the time derivative of your coupling. All right, so I said that the fact that photons follow null geodesics and the fact that the photon number is not conserved because of the coupling will be important, and it is when you look at distances in cosmology. So you know there are there are two broad ways of looking at distances: angular diameter distance or luminosity distances. The fact that light follows null geodesics means that the angular diameter distance will have the same expression as in GR because the reciprocity relation holds in that case. So the angular diameter distance is purely geometrical in that case, and so it follows a law in 1 over 1 plus z times an integral in which you put your cosmology, right? So of course this part will depend on the theory of gravity, on the Lagrangian of the scalar field, etc. On the other hand, because the number of photons are conserved, then the angular diameter distance, which usually stays like 1 plus z, just by conservation of the number of photons along the line of sight, now receives a correction factor in square root of 1 over h, 1 over your coupling, and this is just the coupling evaluated at the time of observation, so say at redshift 0. And we recover the same cosmology factor. Here this is not affected by the introduction of this conformal factor. So what this means is that this eta parameter, which is usually 1 when the distance duality relation is valid, like in GR, and which is just the ratio of this luminosity distance by 1 plus z squared times the angular distance, is no longer 1, but depends on your coupling. Alright, so this is quite simple and well known. And of course you can constrain this eta parameter by measuring distances down the past dipole and transfer that on your preferred theory of gravity in terms of time. So this is, I've quoted here a few constraints. So you see these typically luminosity distance are obtained using supernovae, and angular diameter distance are obtained using standard rulers like galaxy clusters, BA0, in that case, in GR. Usually what people do is to do a parameterization of eta of z. Again, if you want something fairly model independent. The first one is not very interesting, it's having a constant eta. Here we have more interesting parameterization, and just remember for the future that eta 1, eta 2, and epsilon essentially correspond in these various parameterizations to the derivative of the parameter eta at z equals 0. Okay? And so if you look at that, you get constraints on this derivative of eta today of order 10 to the minus 2. Okay? So please, let's keep that order of magnitude of the constraint in mind, because what I want to show you is that actually we can do much better. And why can we do much better? Well, because as both David and Carsten mentioned earlier on, it is known that of course if you couple your electrodynamics to a conformal factor this way, you get variation of your fine structure constant, and indeed it goes like 1 over h. So the variation of alpha here goes like a logarithmic derivative of h times phi dot. So using that, of course, you can rederive that delta alpha over alpha at a given redshift is just your duality, distance duality parameter eta squared minus 1. Right. So if there's no, So in the, sorry, I'm getting confused. Apologies. So in the case of a conformal coupling like this, it turns out that you can relate alpha to eta, and then the variation of alpha is unambiguously related to any potential measurement of violations of the distance duality relation. If there is no violation, if eta is equal to 1, there is no variation of alpha. All right? So using that, of course, as Carsten mentioned, variation of alpha are extremely constrained, in particular at z equals 0, using either laboratory tests or the Doppler experiment, Doppler observation, etc. And so you see that, so here I quote a lab constraint on alpha dot over alpha, well in the lab of course, over the 10 to the minus 17 per year. And that means this translates in terms of the variation of the eta parameter into this. So I don't know why I use this weird value of h naught here, but you can, that's an old kind of value. You can use a more recent, lower value of h naught. It doesn't change the argument, because essentially what you find is that the derivative of eta, remember these parameters, they are the derivative of eta at redshift 0, is now of order 10 to the minus 7, 10 to the minus 8. So that means that any theory of gravity that couples conformally to the electrodynamics would have to satisfy that the distance duality relation cannot be violated by more than 10 to the minus 8. This is 5 to 6 orders of magnitude better than the 10 to the minus 7 that we had, than the 10 to the minus 2 that we had by using simply standard candles and standard modes. All right? So the theory is actually much more constrained observationally by variation of alpha than by cosmological test. All right, so you can also use cosmological constraints on alpha. Again, as it was pointed out, there are various, the blue here are the constraints derived from the VLT and the oranges from the keck, and they disagree. I'm not going to get into which one is correct, which one is not. The idea is that they give an upper bound on variation of alpha anyway, which gives you an upper bound on variation of eta here, and you see that it's always of order 10 to the minus 6. Now, these are interesting because they are weaker than the ones we obtained from lab experiments, but they extend to higher redshift. So that means not only does variation of the distance potential violations of the distance duality relation must be very constrained at z equals 0, but also at much higher z. And typically this comes from quasars absorption lines at about between 0 and 3, 4, I think. So that means you don't have much possibilities to have your scalar field evolve between 0 and z equals 4. All right. Then the next step, of course, is to look at the other place where electrodynamics plays a role, which is in the cosmic microwave backgrounds. So to do that, we have to solve the Boltzmann equations, as Carsten pointed out. So we treat the CMB as a class of photons, distribution function f. And of course we have a Boltzmann equation here. So this is here the UV operator acting on f. And of course, now we have a collision term here that translates the interaction of our photons with the scalar fields. Fixing that C is not, was not completely apparent to me, but actually we can work it around it because we've worked the way the photon number evolves in the geometric optics approximation. So we can force the geometric optics approximation in here and match what the collision term ought to be. So by forcing the geometric optics approximation, I mean we just localize the momentum of our photon in phase space, and then we can derive that the collision term is again quite standard, proportional to f, to p, and then to the logarithmic derivative of the kappa. All right. So if we do that, we end up having a photon number equation which takes this form in Friedman, Bonson, Walker, and the density of photons evolve like this. Now, we wanted to find how the distribution function f evolves with time if you have this sort of coupling. So we parameterized our f as a 1 over exponential p over t plus mu minus 1, where t is the temperature evolving in time, mu is a chemical potential. So this is only approximate, obviously, because the coupling is such that photons are not in adiabatic equilibrium here. The dynamics is not adiabatic, so we would expect further distortions. But because we expanded everything in terms of the coupling, that doesn't introduce much of a difference. So if you do that, you can, by solving the UV, the Boltzmann equation, you can get an estimate of how the temperature of the CMB and the chemical potential at redshift 0 ought to be, and you see that we have here a departure from the standard 1 plus z evolution for the temperature of the CMB. That involves here the coupling at redshift z, the coupling at redshift 0, and the chemical potential is like this. So of course, if the coupling remains constant between decoupling and 0, this is 1, and there's no chemical potential. Oh, thank you. All right. So what is interesting, and I will come back to that in a few slides, but I can mention it already here, is that what we have here is 4 different observables, which are effectively all related. Okay? So there is no choice. Temperature of the CMB, variation of alpha, violations of the distance duality relation, and chemical potentials are all related. Anomalous. And this is independent on your theory of gravity. All right. So, again, for example, it's interesting because if I use the Kobe-Fires bound on the chemical potential, then I can put a upper bound on the variation of alpha at decoupling, which is in a comparable order to the Planck constraint obtained differently. Also, if I parameterize the departure of the evolution of the temperature of the CMB by a parameter beta here, so beta equals 0 if there's no coupling, if electrodynamics is standard, and beta is non-zero otherwise. Well, you see, this is the constraint obtained on beta from Sunyaev-Zeldovich effect directly, and these are constraints obtained on this beta using the link between variation of delta alpha over alpha and T of Z. And you see we are, again, 6 or 7 orders of, well, yeah, well, 6 or 5 orders of magnitude better. So that means just introducing this conformal coupling makes it much harder to fit any theory of gravity to the host of data. All right. But we can do something different. Because we have that, all these things, variation of alpha, violation of distance duality, modifications of the CMB spectrum, are all linked to each other. Effectively, we can perform consistency checks. So typically here, for example, I've rewritten the ratio of the coupling at redshift 0 and at redshift z in terms of eta, quite simple. In terms of delta of alpha, quite simple. In terms of t and mu, not so, in terms of t here, for example, also quite simple. Now that means, if I can measure eta of z, delta alpha over alpha of z, and t of z, calculate these quantities, and compare them, if I have a conformal coupling, including GR, in the case where h is constant equal to 1, then they should all match. Okay? So the contrapositive of that is that, of course, if at a given redshift, it turns out that these 3 expressions do not match, then that means you can rule out conformal couplings. Again, irrespective of the theory of gravity that leads to this conformal coupling. So that's what we've done here. So let me explain a little bit what is represented. So this is the relative variation of the coupling between redshift z and redshift 0 as a function of redshift, obtained from constraint on eta, so measurements of the luminosity distance and angular diameter distance, and from measurements of the T of Z using Sunyaev-Zeldovich at low redshift and spectral lines at high redshift. Of course, because these observations are patchy, they're not all at the same redshift, we've used Gaussian processes to obtain continuous model of the constraint. So the blue area here is the 1 sigma contour for the models, and the red here is the 2 sigma. So that means basically any curve that does whatever it wants in terms of z here that fits into this contour is favored at 1 sigma or 2 sigma. Now, the green line, that's the crux of course, is your variation of alpha. So you see it appears as a line because it's so much better than the other ones. And when you look at current data, there's clearly no region, clearly we're not expecting it, but it's a proof of concept, There's no region where the reconstruction of the coupling from the distance duality relation or the temperature of the CMB do not overlap. So everything is consistent with a conformal factor at the moment. All right? But of course we could ask ourselves, well, how much better do we need to do to try and have the potential to disentangle between conformal coupling or not conformal coupling in the future. So how do we need to improve on that? So as an illustration, I want to show what SK type improvement on eta would lead to. So you see here a redshift about 0.5. We've got a spread here at 2 sigma, which is of order 0.5 on the coupling. Here's what we get from SK type measure of the BAO with 2% expected accuracy on DA. It's very crude because, of course, that should be redshift dependent, and it's not. And we've plotted it around a lambda CDM fiducial model. And basically, we get a reduction of order a factor of 5 if we look at the 2 sigma, a factor of 10 if we look at 1 sigma. So that won't be enough. It would need to go up with extremely good future measurements of T of Z, which we haven't done. But you would expect more and more accurate SZ, and I think it would be interesting to see by how much the SZ would need to improve for us to be able to test these conformal couplings. So I am basically done with the content, so I just want to re-highlight what I said is that irrespective of your theory of gravity, there are at least 4 different observables that are unique, that are modified by this conformal coupling: temporal variation of the fine structure constant, violation of the cosmic distance duality relation, modification of the evolution of the temperature of the CMB with redshift, and of course, a non-Planckian corrections to the CMB. And more than that, is that all these observables are actually related to each other unambiguously. So you cannot just hope to fit one without fitting the others accordingly. And the key here is that in principle, this provides a way of testing conformal coupling to electrodynamics without any assumption on the theory of gravity. So my bet is that, of course, that could be refined by picking up classes of models for the theory of gravity, and the constraint of tests that I showed you earlier on would probably be better because you have more information. Thank you very much.
Questions for Julien?
So you say your constraints is independent of cosmological evolution of the field, but I thought your field needed to evolve in redshift in order to be.
Yes.
So in your conclusion, I didn't understand the logic.
So it's independent on the evolution, but it has to evolve. If it doesn't evolve, then the corrections are 0.
Yeah. So yeah.
But it can evolve pretty much as wishes. So that's a different way of saying that it doesn't depend on the Lagrangian for the scalar field. Right. So if the field rolls into an attractor, or if it runs away, these corrections will be here. These constraints will be. All it will do is it will force a runaway solution to run away in a very safe, shallow potential on this one.
Is it possible to use primordial nuclear synthesis as a test for these conformal couplings as well?
To use
Primordial nuclear synthesis. If you've got a photon number not being conserved, you have a different.
yes, but then you have to go back to the radiation-dominated epoch.
Yeah.
And in that case, my photons will source the gravitational field. And so I cannot now get rid of the theory of gravity.